All right, welcome to 15.8 and 15.9 cylindrical and spherical coordinates for the first time. We will in fact be revisiting these topics at the very end of the class to do some triple integrals, but I just want to present them here at the end of Unit 1 as just an alternative, kind of a new way to think about 3D space. So cylindrical, let's start with. Cylindrical represents kind of the expansion of our old idea of polar coordinates. So you'll be familiar already with the idea of finding some point in polar coordinates using a radius and an angle instead of our good old-fashioned x and y coordinates. But of course, we can always find those. You'll remember that we'll have x equals r cosine theta, y equals r sine theta. And if you wish to kind of go the other way, you can always have, r squared equals x squared plus y squared, and the tangent of theta being y over z, or over z, y over x. We haven't gotten to z yet. Get Mr. Bates. Y over x. All right, well, when we expand into 3D, things actually remain remarkably similar in cylindrical coordinates. In cylindrical coordinates, what we do is we use three coordinates, obviously. We still need three, and they are r, theta, and z. And it's, in fact, the same r and the same theta. So our theta is still measured in the counterclockwise direction from the positive x-axis. We still have an r that comes out some distance in the xy plane from the origin. And then we come up a distance z. So the conversions here are actually fairly familiar. We still have x equals r cosine theta, y equals r sine theta, and z, our z coordinate equals, well, it equals our z coordinate. So in this case, what we have is we still have polar. Use r and theta to kind of come out and locate your point, and then you just move up a distance z to get there. Our other conversions, our conversions back, are unchanged. We still have r squared equals x squared plus y squared, and we still have the tangent of theta as y over x. So let's just quickly sketch some graphs and see if we can work this out. So let's start with r equals 1. What does the graph r equals 1 look like? Well, back in the day, you might remember from polar coordinates that this kind of looked like a circle in the xy plane. In this case, it still looks like a circle in the xy plane, but of course, there's no z coordinate. So it is a cylinder. And if you like, you can turn this into r squared equals 1, which is r squared equals 1 squared. So this is, of course, x squared plus y squared equals 1. We could try another one. We could try r equals z. Or let's try a different one. Let's try z equals r squared. Well, r squared we know is x squared plus y squared. So z equals r squared is, in fact, our good old friend, the paraboloid. So we will often, when it comes to doing other integrals and things, we'll often use z equals r squared. Cylindrical works pretty well for this. I just want to note, both of these are oriented with their axis of symmetry being the z-axis. That's fairly natural for cylindrical coordinates. It actually is a little bit more complicated in cylindrical coordinates to describe things that are centered around the x or the y-axis. The z-axis is kind of taken to be a little bit special here. There's one last one I want to mention, which is just, what if I instead say theta equals pi over 4? It's a little bit of an odd one. So if we come out to theta equals pi over 4, well, there's pi over 4, ish. And you might say, well, let's apply some of our previous intuition. R is missing, so we can in fact be any distance away from the origin that we want. Z is also missing, so we can come up any distance z. And what we in fact get is a plane. We get a plane that's tilted at an angle of pi over 4. that goes through the z-axis. Depending on the book you read and the convention, sometimes people will demand that r be mostly positive, although obviously r can sometimes be negative. So you'll see sometimes that they'll tell you, in fact, you get a half plane instead of, you just get this front half instead of the whole thing. But we know well enough that r can sometimes be negative. So don't be too constrained by that. So we did a couple examples of this in class, and we'll do a lot more. Let's talk a little bit about spherical, because spherical is the more complicated one. So the idea of spherical coordinates is kind of like it sounds, trying to identify points on the surface of a sphere. So the way spherical coordinates works is it's a little bit different. So once again, let's give ourselves a point out here. And spherical coordinates uses 3 coordinates. Once again, it's 3D. It uses rho, which looks like a curvy P, but it is in fact a Greek letter R. So it is rho, theta, and phi, or phi. There's a lot of different ways to write phi or phi. I like, you can kind of do a loose, swoopy one like that. You can do a circle with a line straight through it. You can do a little bit of a tighter swoopy. Any of those are fine. Choose your own adventure here. So in this case, what do these 3 coordinates mean? Well, first of all is rho. Rho, if this is our origin here, rho is the distance from the origin to our point, measured directly. That is, maybe a better way to think about this is that rho squared is x squared plus y squared plus z squared. It's kind of the 3D Pythagorean theorem, 3D distance formula. From there, I'm going to kind of project this point down bloop, 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 onto the xy plane. Theta, as it turns out, is our good old familiar theta angle in the xy plane. It starts at the x-axis at 0 and comes out in the counterclockwise direction. I'm going to pencil in this r, not because this is kind of our good old polar and cylindrical r, not because it's necessarily part of this coordinate system, but it does end up being a little useful. Our last part, phi, is actually another angle, and this one comes down from the positive z-axis. So when phi is 0, we're straight up, and then as phi increases, we kind of come down from the positive z-axis. So the way you locate a point in cylindrical coordinates is you kind of figure out how far away from the origin you're going to be. You turn in theta to find the direction to point, and then you drop down from the z-axis until you hit that point. So things to note here, by the way, are that our limits on phi are usually between 0 and pi. 0 is the positive z-axis, pi is the negative z-axis. We don't usually let it go past pi because kind of at that point it starts to get some ambiguity. It starts to go in the other direction. So we usually limit it that way. So in order to find out, how to do all these conversions and find our coordinates here, we're going to remind ourselves, we're actually going to start with our polar, our cosine theta, and our sine theta. And ask ourselves, what the heck is r? What is this like distance in the xy plane relative to this phi? Well, you can kind of see we have a funky right triangle here. Funky right triangle here. There's a pretty good drawing in your book as well. And a little bit of consideration here can kind of lead you to believe that r is equal to rho sine phi. And one of the arguments here that I always like to make with sines and cosines is, what if phi is 0? Well, if phi is 0, we're right on the positive z-axis. R is going to be nothing. Our point is going to be directly on the z-axis. If phi is pi over 2, then our point's just going to lie in the xy plane. So phi and r will be exactly the same. And that's actually going to give us our full set of conversions here. And they look a little intimidating at first, but don't be too scared by them. So we get x equals rho sine phi cosine theta y equals rho sine phi sine theta, and z equals rho cosine phi. And these are our full set, plus, of course, rho squared is x squared plus y squared plus z squared. And again, if these look a little intimidating to you, I want to remind you that the only time we really ever use spherical coordinates is when things work out to make our life fairly easy. So we will see some examples in class that will be both more and less gross, but it's worth noting we really only dip into spherical or cylindrical coordinates when it benefits us. That's one of the powers of math tools, is that it's a toolbox. We get to use them whenever we want. So let's again look at a couple little samples. So here we'll look at rho equals 1. So what happens when rho equals 1? Well, if our distance from the origin is always 1, it might not shock you to realize that this is in fact the unit sphere. Little unit sphere. This is, of course, the distance from the origin is always 1. 1 here, and 1 here, and 1 here. We could also try something a little unusual as another example, which is phi equals pi over 4. Theta equals pi over 4, in fact, will look exactly the same. Phi equals pi over 4. Well, in this case, if phi equals pi over 4, I'm coming down pi over 4 down from the positive z-axis. And again, let's kind of apply some of our rules, right? You don't see rho, so this line can be as long as short as I want. And we don't see theta, so I'm going to take this and I'm going to spin it around the z-axis. And what we get is phi equals pi over 4 is in fact the top half of a cone. It is in fact the top half of a cone. I guess if you let phi be negative, or sorry, excuse me, if you let rho be negative, it'll be the bottom half of a cone also. But we get the top half of a cone. It's in fact a right cone. There's a little right angle here. It's pi over 4. It's pi over 4. We do in fact get a cone. So you can get some really interesting descriptions of surfaces this way. And I just want to note, again, we're only going to use this when it behooves us. So you will sometimes find, for instance, in our exercises, we will look at in class and in our exercises, what does a plane look like in cylindrical and spherical? What about things not centered on the origin or on our convenient axes? And what we're going to find is that these things are usually gross in cylindrical and spherical coordinates. Like doing a plane that doesn't go through the origin is generally pretty bad in spherical coordinates, which is a way of telling you don't use spherical coordinates for planes. Use Cartesian for that. It's better. All right.